Okay, so in this video, I'm going to go over section 2.4 and 2.5. And then hopefully I'll be able to upload the review video by tomorrow. So 2.4 is all about symmetry of functions. So this is just another property of graphs, not necessarily functions, but all graphs that we can analyze. And when we talk about symmetry of graphs, we're really talking about the same thing you learned in grade school. Like if I had a heart, we learned that the line of symmetry of this heart goes through the middle because there is a mirror image of the left side on the right side. And if I folded that heart over that blue line of symmetry, it would coincide with each other. It'd be exactly the same. So that's essentially what we are talking about here with graphs. So there's three types of symmetry, and that is, the first one is symmetry about the x-axis. The second one is symmetry about the y-axis. And then the last one is when a graph is symmetric about the origin. So we're going to learn about all three of these. So the first one here in this box is talking about when graphs are symmetric with respect to the x-axis. So you see in this picture here of this sideways parabola that this graph is symmetric about the x-axis. So when I say it's symmetric about the x-axis, I mean that the axis of symmetry of the graph goes down the x-axis. So that is the line of symmetry of this graph. And this is the x-axis, but it's also given by the equation y equals 0. Horizontal line at y equals 0. So visually this is pretty easy to see, but I do want to talk about the property of the points on such a graph. So if any point x comma y is on this graph, for example, I have that point x comma y there, then the graph will also have the point x comma negative y, which is down here. So the x values of these 2 points are exactly the same because they line up vertically, but the y values are opposites of each other. So that makes sense. If I'm going over the x-axis and I want a mirror image, it'd be the same distance from the x-axis. And one would just be negative because it'd be below the x-axis for negative y. So points like these are called reflections of each other across the x-axis. And so another example on this graph is it has the point 4 comma 2. And so there would also be a corresponding point 4 comma negative 2. And every single point would have this property. If I picked any point on this parabola, like this one here is 1 comma 1, and then there's a point down here which is 1 comma negative 1. And of course, if I fold that top piece of that graph above the x-axis over the x-axis, it would coincide with the piece below the x-axis. Okay, the next one we're going to talk about is when a graph is symmetric about the y-axis. So of course this means that the axis of symmetry is the y-axis, which is this vertical line. And you can see in this graph that that line does cut this graph in half, where the left is a mirror image of the right. And this equation is given, or this line is given by the equation x equals 0, because it's a vertical line. And so the points on this graph have the property that if the point x comma y is on the graph, so I'll use that point, then the point negative x comma y is also on the graph, because I'm going across the y-axis now, so my x values would be opposite, but the y values would be the same because they line up horizontally. And then there's another point here, 3 comma 4, and so of course the point negative 3 comma positive 4 would also be on that graph. And points like these are called reflections of each other over the y-axis. This is a typo, so this should say y-axis here. Okay. And then the last one that is a little harder to see visually is when a graph is symmetric with respect to the origin. And this one's different because the other two we had like an actual one line of symmetry. But for this one, it's symmetric about a single point, which is the origin in the middle there. So you can kind of think of, I'm just going to use this point here as an example. So if I look at this point and I think about reflecting it over the origin, well, of course, I have to go towards the origin, and then you see that it does line up with this point over here. But that changes depending on where you are on the graph and what point you're looking at. So if I pick this point and I reflect this point over the origin, well, now I have to go towards the origin this way, and now this point is equal distance from the origin as the other one. And so that is a mirror image. So every single point has a mirror image of that point over the origin, but it just has a different line of symmetry for each point. So let me erase those. Okay, so more algebraically, technical definition is that for any point on the graph, and here I'll use this one again, y comma x, then the point negative x negative y is on the graph. And so both the x and the y values change. And that's true for any point on a graph that is symmetric with respect to the origin. So if this graph has the point negative 3 comma square root of 7, then the point positive 3 negative square root of 7 would be on the graph, because those, the x and the y value there are both opposite. Visually, if I take this entire graph and I rotate it 180 degrees about the origin, then the resulting figure will coincide with the original. So if I take all that entire red graph and rotate it about the origin 90 degrees, then we would end up with the same function. So if you can visualize that, then that's another way that you can tell. But you can always use the relationship between the 2 points up here, between all pairs of points on the graph, to determine whether a graph is symmetric about the origin. Okay, so we do have algebraic tests to determine symmetry with respect to the x-axis, the y-axis, and the origin. So we're going to talk about that. So the first one is the test to test whether a function is symmetric about the y-axis. So if you remember, if it's symmetric about the y-axis, then my y values will change because I'm going over the x-axis. So the test involves replacing y in the equation with negative y. And if we do that and it produces an equivalent equation, then the graph will be symmetric with respect to the x-axis. And then for the y-axis, to test for symmetry about the y-axis, our x values are changing if it is symmetric with respect to the y-axis. So I'm going to replace my x in the equation with negative x, and if that produces an equivalent equation, then it will be symmetric with respect to the y-axis. And then finally, to test for symmetry about the origin, we replace x with negative x, and we replace y with negative y. So we have to replace both. And if that produces an equivalent equation, then the graph will be symmetric with respect to the origin. So for this first example, they want me to test whether y equals x squared plus 2 is symmetric with respect to the x-axis, y-axis, or origin. So we're going to do all three. So if I test for the x-axis, again, I'm replacing y with negative y. So this y will become negative y equals x squared plus 2. And now to see if it's the original equation, if it's equivalent to the original, and this is the original, I need to solve for y. I need to get y by itself to see if they're the same on both sides. So I would have to divide everything by that negative 1 in front of y to get y by itself. So this will give me y equals negative x squared minus 2. And this is not the same as the original because the x squared and the 2 are both negative. The original were both positive. So this is not symmetric about the x-axis. Because it's not the same as the original. And now we will test for symmetry about the y-axis. So I'm going to replace the x in the original up here with negative x. So that would be y equals all negative x all squared plus 2. So just remember, if you're plugging negative x into something being squared or cubed or have an exponent, you have to put it in parentheses. And then negative x squared, that will remain positive x squared. So this will result in positive x squared plus 2. So this is the same as the original. So this is symmetric about the y-axis, since we got an equivalent equation. And then finally, we will test whether it is symmetric about the origin. So I would replace both now. I'm replacing y with negative y and x with negative x. So this would be negative y equals negative x squared plus 2. And we already know, I'm going to bring the negative y along, and the negative x squared will become positive x squared plus 2. And then this is exactly where we were up here with the test for the x-axis. So I would have to divide everything by negative 1, and of course we already know, because we already did this, that this does not produce an equivalent equation. This is y equals negative x squared minus 2. So not symmetric about the origin. Okay, so these are the like the less common tests that you'll be using. Now, if you wanted to test for of an equation for symmetry about the x-axis, you have to use this test. But I am about to show you another test that also tests for symmetry about the y-axis or the origin. And that's on this next page here. But these are only for functions. So if if a graph is symmetric about the x-axis, let me give you an example, same example as before. This is symmetric about the x-axis here in this picture I'm drawing. This graph is not a function because the x values would be repeating. So that fails the vertical line test. This is not a function. So that's why the test for symmetry about the x-axis is not included here, because these are only for functions. So these are only used to test functions to determine whether they're symmetric about the y-axis or the origin. And we have a special word for functions that are symmetric with respect to the y-axis. Those are called even functions. So if it's a function is even if it's symmetric with respect to the y-axis. And a function is called an odd function if it's symmetric with respect to the origin. Excuse me. Okay, so the first test to test whether a function is even is actually exactly the same as what we did for the previous test to determine whether a graph was symmetric about the y-axis. And that is, we are going to plug in negative x for x. So that's what we just did on the test for symmetry about the y-axis. We'll plug in negative x to the function, and if that results in a equivalent function, if it results in the function we started with, which is f of x, then that function is even, which means it's symmetric about the y-axis. So that's the same exact test we did on the previous page. But the other one, to test whether it is an odd function, this one's a little different, but it's pretty much the same thing in disguise, but it's just a little different. So for this one, we're still going to plug negative x into the function. And if we do this and it results in the negative version of the original function, which is the same thing as if it equals -1 times f of x, this means the same thing, then we can determine that the function is odd. Okay, so this note here says that except for the function f of x equals 0, a function cannot be both even and odd. So if you do the first test and it's even, then you don't need to continue to test for odd. So let's do this first example here. So it wants me to determine whether the function is even, odd, or neither. So I'm going to plug in negative x into this function. I'm going to find f of negative x. F looks a little bit weird. And again, this notation tells me to plug negative x into this function everywhere I see in x. So this would be negative x all raised to the 5th power plus 3 times negative x all raised to the 3rd power minus 2 times negative x. And if you remember, anytime you raise a negative number or variable to an odd exponent, this will remain negative. So this would equal negative x to the 5th. And then here, negative x cubed, again, that's an odd exponent. So that will be negative 3x cubed, because positive 3 times negative x cubed is negative 3x cubed. And then negative 2 times a negative x will be a positive 2x. So this is what we got when we plugged in negative x. So now I'm going to compare to the original. So the original first term was x to the 5th. And this one is negative x to the 5th. So that's a different sign. 3x cubed was positive. Now it's negative. And then 2x was negative. And now it's positive. So all of these signs changed. And so this is the same thing as -1 times the original. Okay. If I took this function up here and I multiplied it by -1, I would have to distribute it, and all the signs would change. So when all the signs change, in each term, then the function is odd. That's the second case. It equaled negative f of x. So this function is odd. And therefore it is symmetric about the origin. All right, and then the last video says to determine whether the function is even, odd, or neither. So again, we're doing the same thing. We're going to plug in negative x into this function. So this would be 3 times negative x all squared minus, and then I'm plugging in a negative into that x, so that'll give me 2 negatives there. Negative x cubed, and then plus a negative x. So the first negative x squared, that'll change to positive x squared. So that would be 3x squared. This negative x cubed, since that exponent's odd, it would remain negative x cubed, but then I have another negative here, so it'll change it to a positive x cubed. And then this would just be negative x. Plus and negative x is the same thing as minus x. So this is my end result after I plugged in negative x. So now I go and I compare. So the first term was a positive 3x squared, and that's still positive 3x squared. But the second term was negative x cubed, and this one's positive x cubed. So that sign changed. But the first one was the same. And the last one's the same, different as well, because it was positive, now it's negative. So both of these are different signs. That's how I'll write it. So it's neither, because not all the signs are exactly the same, and it's not the exact same function. And they're not all opposite signs. So this is neither. Okay, so that's the end of 2.4. So I'm going to move to 2.5. Okay, and if you're looking at my files that I upload in Canvas, they're under the files in Canvas, then you would have already noticed that I gave you this library of functions in 2.1. So I introduced them there. I don't think did I make a video? No, I only made 2.2 and 2.3 for my online class, but if you were in my in-person class, then you would have gotten this in the notes for 2.1. But here they are again, because this is when we are really going to be using them. So 2.5 is all about the transformations of functions. And so we're going to be using these functions to build other functions by either shifting them horizontally, vertically, or stretching or shrinking them, or reflecting them across an axis. So all of those that are italicized, these are called transformations. So we're going to be learning how to do this. First, I kind of just want to review even, odd here. So the line, if I just looked at this first graph here of the line, this graph is going to be symmetric about the origin, so it's odd. Because again, if I pick, it's definitely not symmetric about the x-axis, because it would have to be a mirror image over the x like that. Or if it was the y-axis, it'd be a mirror image like that. But it's not. It's going through the origin. And if I pick a point here and I reflect it over the origin, it will end up over here. So that is symmetric about the origin, so it's odd. The next one is has symmetry about the y-axis. So this one is even. The square root function is neither. It's neither even nor odd. It doesn't have any symmetry. The cubing function is odd. It is symmetric about the origin. If I pick a point here and reflect it over, then it would end up right here. And so that is symmetric about the origin. Oh, I did that. And then the next one is also odd. The cube root function. The next one is also odd. And the last one is even. So I just kind of wanted to show you that, just kind of go over that so you could kind of get an idea of how to identify that visually. All right, so now back to transformations. So again, I'm going to erase this so I can come back up here and use this. We're going to be using these base graphs. So you need to get real familiar with these base graphs and the ones that you will see on your test. So the ones you really need to know is this one, this one, this one, and this one. Those are the ones you'll see the most used on your exam. And on your little flashcard, you can sketch a picture of these base graphs if you want, but you just can't have any examples using the transformation for them. I'm sorry, I can't quit yawning. Okay, so the first one we're going to go over are vertical translations. And so the definition of that says that for a b greater than 0, the graph of f of x plus b, and here I want you to know that when they say f of x, they're talking about one of these base graphs. Okay, so for example, well, I'll show you this example down here, but it could be x squared plus some number, or the square root of x, and then plus some number, but one of our base graphs, that's what they're talking about with the f of x. So if I have a constant and I add it to one of our base graph function equations, then the new graph of this f of x plus b will be the graph of the base graph shifted up b units. Okay, so for example, in this picture down here, the one in red, this is the base graph, f of x equals x squared. It's the squaring function. And that's the parabola in red that you see with the origin or the vertex at 0, 0 at the origin. And then the blue is the graph of f of x plus 2. And I'll write what f of x plus 2 is over here. This would be x squared plus 2, because f of x is the base graph that I'm using here in this example. So you see the blue graph, it's the same parabola, but it's been shifted up 2 units. So now the vertex is at 0, 2. And all the points from the red graph will be shifted up 2 units to create that blue graph. And then the next definition is for b greater than 0, the graph of f of x minus b is the graph of f of x shifted down b units. So now that is the picture of the green graph, which is f of x minus 2. And f of x minus 2 is x squared minus 2. So that took our parabola x squared and shifted it down 2 units, every single point. So now everything's shifted down 2 units. Excuse me. Okay, next is horizontal translations. So the definition here says that use a color. For b greater than 0, the graph of f of x plus b, so now it's like f of x plus b, which is inside the parentheses, which means it's being added directly to the x, not to the entire base graph, but directly next to the x in the function. And this would be the graph of the base graph shifted left b units. So let me explain this one. So here in this example graph, the one in red is our base graph, f of x, and this is the base graph of x cubed. If you look back at the library of functions, this is the x cubed one. It does that weird little like curly thing at the origin. And so the one in black, this has been shifted to the left 3 units. Because if you look at the one at the origin in the red right here, then I would have to count to the left 1, 2, 3 to get to that new point. So that one in black has been shifted to the left 3 units. So this would look like, this would be f of x plus 3. And f of x plus 3 is equal to x plus 3 all cubed. So now the plus 3 is inside next to the x directly. And that would all be being cubed, as opposed to x cubed plus 3 on the outside. That's the difference there. So when it's being added directly to the x, it's going to affect my horizontal movement. It's going to shift it horizontally. And with the x values, it's like kind of counterintuitive. So you'd think that if you added 3, it would move it to the right, but it's actually counterintuitive, so it moves it to the left when you add. And then the next one is when we have a b greater than 0 and we subtract b directly from the x in a base graph, then that would be the base graph shifted to the right b units. And so that's what we see in purple. This is f of x minus 3, because now it's been shifted to the right 3 units from the original base graph of the red one. It's shifted to the right to get to here. And all the points have shifted to the right on that function. And f of x minus 3 is equal to x minus 3 on the inside all cubed. And again, I'm just using, random base graphs for these examples, but this is true for any base graph. For absolute values, square root, it works the same way. Okay, the next one, type of transformations are reflections. So for this one, when we have a graph, y equals negative times a base graph. So when there's a negative on the outside and front of the entire base graph, then this is the graph of the base graph, f of x, reflected across the x-axis. So let's look at this example. Here, the base graph is the one in purple. And that base graph is the square root function, square root of x. That's what you see in purple here, just that part. And so the one below it has been reflected over the x-axis because all those points went over the x-axis. And so that function is equal to negative f of x, which is equal to negative square root of x, since square root of x was our base graph in this example. And then the next one is when we multiply the x directly by a negative, or sorry, multiply a negative directly to the x in our base graph. So when we have something like this would be the base graph reflected across the y-axis. And so that's what we see here in red. If you compare it to the purple graph, which is our base, that is being reflected across the y-axis from the purple. So this is, where's my wrong thing? This is equal to f of negative x, and f of negative x is equal to the square root of negative x, where the negative's on the inside, directly touching the x. Okay. So I'm going to do this example, and then I have kind of like a 2.5 part 2 that's kind of short. So, but this example says to use transformations to graph the function. So sometimes they'll give you multiple transformations in one. So there's two transformations in this function. The first is the -5, and the second is the negative on the outside. And the first thing I would need to know is what is the base graph that they're using, that they used to build this. So I think about my my library of functions, and I compare with the equations. And let me just go back to that. So the squaring function is x squared, square root of x, x cubed, or absolute value of x. I'm just looking at these right now. So if I go back here, this equation up here has an exponent of 2. So the only base graph I know that has an exponent of 2 in it is x squared. So therefore my base graph would be x squared. So that's the first thing. And then I have two transformations in this function. The first one is going to be the one in green that I highlighted. And that is a horizontal shift And remember, I said if it's directly to the x, it's kind of backwards intuitive. So I'm subtracting 5. You'd think that maybe would move it left, but actually it moves it to the right. So this is a horizontal shift to the right 5 units. And then the second one is the negative on the outside in front of the entire function. So this is affecting my output values. Like after I plug a value in x and I do that, then it'll get multiplied by negative. So that's affecting my output value. So it's changing my y values, which means it's a reflection over the x-axis. So this is a reflection across or over the x-axis. Okay, so to graph this, I'm going to start by doing each transformation at a time. So from my base graph. So we start with this in our graph, and then we follow the transformations until we get the final answer. Now, we'll say that the order does matter when you do these transformations, and to be safe, you always want to start with the transformations closer to the x. So if there's something being added or subtracted within the parentheses or directly to the x, you want to do that first. That's why I put the horizontal shift first, and then you work your way out. So the negative on the outside, I would do that next. So again, what do I mean? I'm going to sketch, and I should have put a graph here, but I didn't, so I'll just sketch it. First thing I'm going to do is sketch the base graph, which is the parabola. X squared is the parabola, where the vertex is at 0, 0. And then I'm also going to find just a couple other points on this base graph so I know how to shift my points. So if I plug in 1 to x squared, I get 1. So this would be a point, 1, 1. If I plug in negative 1, I also get 1. So that would be the point negative 1, 1. So just find a couple points so that you can easily shift those points as needed. So this is the base graph, x squared. And then the second thing I'll do, I'll sketch another graph. And again, you can do this on your paper, like when you take the test, and show me your work, like you should. And so now I'm going to do the horizontal shift. So I'm going to look at my base graph I have graphed, and I'm going to shift all those points to the right 5 units. So the point at the origin, the 0, 0, will now be at 5, 0. So it'll be right here. The point 1, 1, sorry. If I shift that to the right, that would now be 6, 1. And then negative 1, 1. If I shifted negative 1 on the x 5 units to the right, that would become positive 4, 1. So this is what it looks like when I just shift my graph to the right 5 units. So this would be y equals x minus 5 all squared. And then finally, I want to do the final graph, which would actually be my final answer. and I want to do the reflection. So again, I'm doing it from this second graph I just made, and now I'm reflecting all of those points across the x-axis. So when you reflect across the x-axis, your y values turn to negative of all your points. So the 5, 0 would actually stay the same. Oh, let me write that above. But the 4, positive 1 would become 4, negative 1. And the 6, positive 1 would become 6, negative 1. And then this would be it. So this is my final graph they wanted me to find. Final answer. Oops. This is what you would actually graph. So you can, always do these by hand on paper, get a good idea, and then graph the final one in Pearson. Okay, so I'm going to switch to the last one of 2.5. I just have it on a separate document, so give me 1 second. Here it is. Okay. All right, so this is still 2.5. Again, I just separated this. So the next type of transformation, these are vertical stretching and shrinking. So you don't have to worry about these for the exam. Everything prior to this one, you will have to worry about the exam, but these stretching and shrinking ones, they won't be on your exam. So the first one says that the graph of y equals a times f of x. So when we multiply one of our base graphs by a constant a on the outside of the base graph, then what that does is it stretches vertically, stretches my graph vertically whenever that constant, the absolute value of that constant, is greater than 1. Okay, which really just means it's not a fraction. It's greater than 1. But it'll shrink it vertically if that constant, the absolute value, is between 0 and 1. So that would be a fraction. Now, you think about stretching vertically. So for example, if I had a circle here, and I told you to grab the top of the circle with your hand right here, and I told you to grab the bottom of the circle with your hand, and then I told you to stretch it vertically, which would be up and down. So you're stretching it. That would cause your circle to become like this, right? Get taller, or maybe even like this, I should say. It'd get taller and more narrow if you stretch that out with your hands, like a rubber band. If you stretch the rubber band vertically up and down, it will get narrow. And then if you shrink it vertically, which means now you're pushing down on that circle with both your hands, so you're shrinking it vertically, well, then it would kind of look like, erase this. If I push that down, then it would kind of go out like this, right? Just like a rubber band. So that's kind of like what you want to think of when you're just trying to wrap your mind around what that even means. So let me erase that. Okay. And then algebraically, we can also determine what the new points will be algebraically using this little note here. So this says that the y-coordinates of the graph, only the y-coordinates, the x-coordinates will still stay the same, can be obtained by multiplying the y-coordinates of the original base graph by a factor of a, whatever that number a is. So let's look at an example. So this one is the base graph being used in this example, and that is the absolute value of x, if you look back at your library of functions. The one in blue, this is the one that's being stretched vertically, and it's being stretched vertically by a factor of 2. So this is 2 times f of x, which is equal to 2 times the absolute value of x. And as far as the points go, if you look at a point on the original base graph f of x, this point is 2, 2. Well, just like following that red rule up here, to find the coordinates of the new one, the x value will stay the same here, but I would multiply that y coordinate of 2 by 2, and that would give me 2, 4. So I am multiplying by the factor of this 2 here. And then similar, there's another point over here that is -2, 2. And so if I just multiply that y coordinate by 2, I would get -2, 4. So the x values are not changing, but the y values are being multiplied by a, whatever the number in front of the base graph is. And then the one in green, this is the graph of f of 2 times, I'm sorry, that's wrong. This is the graph of 1/2 times f of x. So this is the second case. It has been shrunk vertically. So this would be equal to 1/2 times the absolute value of x, would be the equation of that function. And so again, if I found this point here, the x value would be the same, but the y value would be, to get to that y value, I would multiply the red y value of 2 by 1/2. 2 times 1/2 is 1. So that point is 2, 1, and the other one is 2, -1. Or, my bad, -2, 1. Okay, and then the last transformation that we have is when we stretch or shrink horizontally. So this happens whenever we multiply the x in the base graph directly by a constant. So now the constant's being multiplied directly to the x, not the entire function, just the x in the base graph. And so it shrinks horizontally whenever the absolute value of that constant's greater than 1, so not a fraction. But it stretches horizontally whenever that constant, the absolute value of that constant's between 0 and 1. And the reason why the absolute value is on both of these rules, and there is a note below I forgot to read, But up here, I'll go over that real quick. If it's a negative number, the negative, if a is less than 0, let me use a different color. The negative just represents the reflection across the x-axis, because that would be negative f of x. But the number is what we use for the stretching or shrinking. And for this one, if c was negative, well, this would be reflected across the y-axis, because this would be f of negative x. And then if there was a number there, the number would represent the shrinking or stretching. So just be aware of that. Okay, so with this one, we can get the new points by taking the x-coordinates. So now we're only going to be changing the x-coordinates because this is a horizontal stretch. And the previous one was a vertical stretch, so we would be changing the y-coordinates. But now we're just changing the x-coordinates by dividing the x-coordinates of the base graph by a factor of c. So now we're dividing, not multiplying. So in this example, my base graph here again is the absolute value of x. And these actually look exactly the same. But I still use this example to show you how this works. And the blue graph, this is an example of shrinking it horizontally. And it's being shrunk horizontally, again, by a factor of 2. And so this would be f of 2 times x, which is equal to the absolute value of 2x. And so if I pick a point on the original, this point's 2, 2. To find a new point, now I'm changing the x value. The y value stays the same. But I'm changing the x value by dividing by whatever number is being multiplied here, which is 2. So 2 divided by 2 is 1. So that's how we get this point here, 1, 2. And then on the other point, this is negative 2, 2. So if I divide that x value by 2, I get negative 1, 2. And again, this is a horizontal shrink. So let me do my little circle example here. If I have a circle and I tell you to grab it on the left and the right, and I tell you to shrink it horizontally, that means to push it in. So it would get narrower, look like this. Same thing as a vertical stretch. But this is a shrinking horizontally because now I'm pushing it in and it's getting smaller. And then if I still had my same hands there where I have them in blue and I tell you to stretch it, then it would look like this. Get wider. So that's just kind of how you can think about that. Okay, and then the last example here is the green graph. So this is the one that's being stretched horizontally. It's getting wider. And this is being stretched by a factor of 1/2. So this would be f of 1/2 times x, which would be the absolute value of 1/2 times x. And so on here, I actually didn't include them on the graph. But to change the x value here, I would have to divide the x value of 2 by 1/2, and that would give me 4, which would be here. And this one would be over here, which would be negative 4. Okay, so all of those points I have, they all have the same x value. or I'm sorry, y value, but the x values are changing by a factor of, well, really by dividing the x coordinate by the c, whatever number is being multiplied. So on this is the last page I have, and then I'll be done. This is important because these are a couple examples of transformations, but this is starting your test review. So test 1 review questions. These are the type of reflection or transformation questions that you can expect to see on your test. So I wanted to talk about them. So the first one says, describe how the given function can be obtained from one of the basic graphs, then draw the function. So they give me this function g of x, and what it's going to do is it's going to kind of walk me through this problem on the test. So it says start with the graph of f of x equals, and this is where they want the base graph. What base graph did they use to build this function? Well, if I look back at my library of functions, the only one that has a square root in it is the square root of x. So this base graph is the square root of x. So that's the answer that would go right there. And then it says shift it blank 3 units. So when I look at the 3, I see the 3 they're talking about. It's being subtracted directly to the x underneath the square root. So when it's happening directly to the x, that's a horizontal shift, and this is the one that's counterintuitive. So because it's being subtracted, it's actually going to go to the right. So this is shift it right 3 units. And then shift it blank 2 units. So I see the 2 they're talking about. And this is being added to the entire function on the outside. So this is a vertical shift. And that one is just like it says. If it's being added, then it goes up. So this is shifted up 2 units. And then they want me to graph this function. So the first thing I'm going to do is sketch over here. Let me make that a little bigger. The base graph of the square root of x. And that starts at the point of the origin, and then it goes like that. And I can find a couple of other points on there. If I plug 1 into the square root of x, that gives me 1. If I plug in another x value, I'd want to pick like a perfect square root. So let's say 4. If I plug in 4, the square root of 4 is 2. So the y value would be 2. So that would be 4 comma 2 for that point, 1 comma 1, and then the origin of 0, 0. So I have 3 points on my base graph of the square root of x. And then I would want to do the minus 3 next. So the minus 3, like we said, shifts it to the right. So actually, let me move this over a little bit. Shifts it to the right 3 units. So the 0, 0 would end up being at 3, 0. The 1 comma 1, if I shifted that to the right 3 units, that would be at 4 comma 1. And then the 4 comma 2 would end up at 7 comma 2. So it looks like that. Basic, just a little sketch. So this would be the graph of the square root of x minus 3. And I'll just use y equals just to... Okay, and then I still have one more transformation to do from this graph, and that will be my final answer, so I'll graph that on the actual graph now. So now I'm going to take all of those points I just found in this graph and shift them up 2 units. So the 3, 0 will become 3, 2. So that would be right here. The 4, 1 would become 4, 3. And the 7, 2 would become 7, 4. And that's what that would look like. So that's my final answer. Okay, then number 2 says write an equation for a function that has the graph with the shape of y equals x cubed, but shifted to the right 5 units and up 6 units. So now they're giving me a base graph of x cubed, and they want me to find the new graph that used that x cubed and shifted it right 5 units and up 6 units. So if I want to shift it to the right 5 units, this would be subtracting 5 from the x. So that would be x minus 5 all cubed. And then up 6 units, this would just be adding 6 to the outside of the function. And then that's it. So this would be the answer for that type of question. And then the last one says, write an equation for a function that has the graph with the shape of y equals the square root of x, but reflected over the x-axis and then shifted down 2 units. So I'm just going to use the green for the reflection, shifted down 2 units. So now they're giving me the base graph of the square root of x. And they want me to reflect it over the x-axis. So if I reflect it over the x-axis, my y values would change. So that negative needs to be in front of the entire base graph. So that'd be negative times the square root of x. And then shifted down 2 units. This would be minus 2 on the outside of the base graph. That's a vertical transformation. So you can write these transformation rules on your flashcard. You just can't have any worked out examples. But any of these rules you can have on there. Like this one, these. You can have those as long as you understand what they mean. But you can't have any examples. And remember, you do have to send me an email if you're in my online class, a picture of your flashcard and have me approve it, or they will probably give you trouble at the testing center. And also make sure you make your testing appointment if you're taking your test in my online class. Some of you still have not done that. And if you wait till last minute, you're not going to have an appointment opened, and then you will not be able to take your exam. All right, so email me if you have any questions. You guys have a good weekend, and I'll be posting the rest of the exam review tomorrow.